Okay. So last time we used the TDS equations to to derive expressions for change in specific entropy for two special cases: incompressible materials, so liquids, and ideal gases. Um, so last time. Before I get going with this, we're going to have quizzes next week. So statics quiz on Monday for the people who care about that, and then quiz in this class a week from today. Okay. So last time we derived from the TDS equations uh, the ds is equal to CV dt over t plus r d little v over little v. And ds is equal to Cp dt over t minus r dp over p. And these are relevant for ideal gases. Okay, and these are very accurate. The problem comes from when you go from this to integrating it. How do you integrate this? For smallish temperature ranges, you can assume that CV and CP are constant. And if you do that, it makes the integration easy because you can pull those constants outside of the integral. And so it gives you that the change in specific entropy is equal to CV times the natural log of T2 over T1 plus R times the natural log of V2 over V1. And you can do the other one the same way. So another way to express this change in specific entropy is integrate that second one, and you get Cp natural log of T2 over T1 minus R times the natural log of P2 over P1. So all that is just, that's doing those integrals, assuming that all those, that the CPs and CVs are all constant as the temperature changes. But really, CP and CV vary with temperature.
Professor?
Yeah.
So T is temperature, right?
Right.
And is V specific volume?
Specific volume, that's right.
And P is just pressure?
Yep, that's right. And those derivations are 4-line derivations or something like that. We went through them last class, so you can look back at that. And so if CV and CP vary with temperature, I mean, look at these first terms of these ds expressions. You can still integrate those with respect to temperature. It's just uglier. Okay. And you just need to know a polynomial representation for CV or CP. Okay. Um, and the way that we can do that, I mean, I could give you the coefficients of the polynomial, but instead of that, you can look up uh, in ideal gas tables um, an expression like this. So this is just taking the second of these two expressions, and um, we can write it as this function s super 0 of t2 minus s super 0 of t1 minus r natural log of p2 over p1. You could do it with volume too, but well, let's put it in there. Sorry to mess up your notes. I'm going to move this down. And so you could also write this as delta S is equal to S super 0 of T2 minus S super 0 of T1 plus R natural log of V2 over V1. Okay, so those S super 0 functions are just doing the integration for you where CV and CP are not constant. Okay, so you would look up S super 0 at each temperature in an ideal gas table. Um, that just calculates the integral of this first term, So S super. Oh, those are different things. So shoot, that's why I didn't have both of them in there. S super 0. Well, dang it. Let's get that back out of there. So what a mess.
Let's forget the last 2 minutes.
Yeah. I need a video editor. Okay, so let's go with that. So what S super 0 is, I mean, they just have gone and calculated these complicated integrals for you where CP is expressed as a polynomial function at temperature. Okay. And so let's see what that looks like in an ideal gas table. So if you go to the tables, so we have one, air is an ideal gas. Okay. And again, like the regular tables, you have to look these up. Like you have to have a table for your specific ideal gas. This is really the only ideal gas we tend to use. But in here, you can look up for a given temperature. Here's our value of S super 0. So you can just look it up and get a slightly more accurate value than you would using these two things. Okay. Well, there's one case where these two expressions are the same. So the change in specific entropy expressed as, CV natural log T2 over, let's do this as CP, natural log of T2 over T1, minus R, natural log of P2 over P1 is equal to S super 0 at T2 minus S super 0 at T1 minus R times the natural log of P2 over P1. And that's the isothermal case. Because in that case, those temperatures are the same, so this term goes away. S super 0 is the same for these two temperatures, so these cancel, and you just end up with, delta S is equal to negative R natural log of P2 over P1. Or in other words, R natural log of P1 over P2. I'm not going to box that. So this is true for isothermal only. So anytime you see a problem where you're trying to calculate a change in specific entropy for an ideal gas, and the problem says that the temperature stays constant or it's isothermal, then this gives you a perfectly accurate calculation without having to go to the ideal gas tables. So I think like one of the problems I'm going to assign for today asks you to, you have to calculate the change in specific entropy. It's talking about an ideal gas that isn't air, okay? But since the temperature stays constant, you get perfectly accurate results.
So R is what kind of constant?
That is the gas constant for that specific gas. So, and that is the universal gas constant divided by the mass per mole. Okay. So that one doesn't vary. That just has to do with what gas you have. Okay, let's do an example. So let's say this is air, and let's say that at state 1, we have a temperature of 300 Kelvin, a pressure of 1 bar, and then this process takes us to state 2, and we have a temperature of 1000 Kelvin and a pressure of 3 bar. And we just want to calculate the change in specific entropy. So we're going to do it two different ways. First, we're going to assume that CP is a constant value of about 1.005 times 10 to the third. We're going to assume that that's just constant over our temperature range. And then second, we're going to use the S superscript 0 from the air ideal gas tables. Um, 300 to 1,000 Kelvin looks like a pretty big temperature range. So you might expect that our approximation from part A is going to be pretty bad. It's actually surprisingly good, but we'll see that it's off a bit. I think it's around 10% if I remember right. So I mean that's an important difference, but you can certainly still get a ballpark idea from this calculation. And then second, this is air, so we happen to have the ideal gas tables for it, and so we can just look up these S super zeros. Okay, so for part A, um, well, what we have is two pressures. So what we want to use is the pressure version of this expression for delta S. Okay, if we were given volumes instead, we would use the volume version. So we're going to use that the change in specific entropy is equal to the natural log of T2 over T1 minus R times the natural log of P2 over P1. And I left off the CP here. So the change in specific entropy is equal to 1.005 times 10 to the third times the natural log of 1,000 divided by 300 minus, we use an R value for air of 287 in SI units. And you get that by, we've done that in class, but you get that from the universal gas constant divided by the molar mass in kilograms of a mole of air, which is like 80% nitrogen, 20% oxygen. Okay. We've done that enough though that I'm just going to use the value of 287 in SI units times the natural log of 3 bar, 3 times 10 to the fifth, divided by 1 bar, 1 times 10 to the fifth. And we get a delta S value of 894.7 joules per kilogram Kelvin. Okay, the second way we're going to do this is delta S is equal to S super zero of 1,000 minus S super zero of 300 minus 287 times the natural log of 3 times 10 to the fifth pascals divided by 1 times 10 to the fifth pascals. And you can look up these values, I think, and hope that those are values that are just given in the table. Otherwise, you'd have to do interpolation to use this. But okay, we have 1,000. So 1,000 S super zero in, let's see what units. It's in kilojoules per kilogram Kelvin. So whatever it says, we have to multiply by 1,000 for SI units. But 2.967, I'll just call that 2.97. And then for 300, we have 1.70. So delta S is equal to 2.97 times 10 to the third minus 1.70 times 10 to the third minus 287 times the natural log of 3 when you do that division. And you get that the change in specific entropy is 952.7 joules per kilogram Kelvin. Okay, so if we think of, so which of these two would we think of as right? You know, if we're going to figure out the percent error in the other one, which one of these do we expect to be more accurate? Yep. Yeah, B is the one we expect to be more accurate. So to calculate the percent error, we'll take the difference between those two. So 952 minus 895, or 953 minus 895. So the difference is 58. And then we'll divide that difference by the one we expect to be right, 953. And you get about 6% error. So part A only gave us about 6% error for this temperature range of 700 degrees Celsius. That's pretty good. On tests, I'm never going to ask you to look up those S super zero values. I'm only going to ask you to do that log calculation. So on exams, I'll never ask you to go the S super zero route. But it's important to know it's there, and I think there might be a problem or two on the homework that you have to do that. Any questions about that? Okay, so that's ways to calculate the change in specific entropy. We've done it for incompressible materials, and we've done it for ideal gases. The next thing I want to talk about is entropy production. And you can think of this as inefficiency introduced into a cycle, or not a cycle, into a process. Could be a cycle, but it doesn't have to be. Okay, so the change in extensive entropy, so this isn't specific entropy anymore, you have to multiply by the mass to get this, is equal to the integral from state 1 to state 2, come in, of all of the heat transfer divided by the temperature around the whole boundary, plus some value sigma. It's kind of the same idea as we saw in the Clausius inequality.
What about the interval? Is it supposed to be state 1 to state 2 or state 2?
Yeah, you're right. It's state 1 to state 2. Thank you. That would be pretty boring this way.
Would that be just like an instant or?
Yeah, it would just give you 0, just nothing happens. Uh, Okay, and this sigma has to be positive. Okay, so um, let's try to wrap our heads around what this is saying for a second. Uh, Forget about that sigma for a second, and this looks very much like the definition of entropy. Okay? But there's one difference between this, a key difference between this and the entropy definition. This integral in the definition of entropy um, is for a internally reversible process, for like a perfect process. Okay? In this case, we're talking about the actual process, not an ideal process. Okay. Um, and so if you think back to the Clausius inequality, you know that for a cycle, if you do this integration for an actual process, you get something that's less than zero, right? That's what the Clausius inequality says. And if it's equal to zero, uh, then you know that that's an internally reversible process. Okay. Well, so what we're saying here is not necessarily for a cycle, but you can sort of think we'd have something less than zero for an actual process, something equal to zero for a perfect ideal process. And so the difference between those is this sigma. Okay. And whatever sigma is, that's entropy that's introduced by the system. And so that's like entropy that's caused by inefficiencies in your process. Okay. So the bigger sigma is, the less efficient that actual process is. Okay, so uh, let's do an example and calculate produced entropy. Um, so let's say we have a gearbox. It's just this closed box. We've seen something like this before. Um, and inside there are two gears in contact with each other. Um, and we'll turn this one with a power of 60 kilowatts. And the output result will be, well, if this one in our view is going counterclockwise, the teeth on the bigger gear here are going to turn the little gear clockwise. So that's going to go the other direction. And let's say that this is 58.8 kilowatts. And let's say that this process is steady state, which means that at every instant you can think of like any amount of time you want to look at, you can think of it as a cycle. And let's say that at the boundary of this gearbox, um, the temperature is 300 degrees Kelvin. which is a little warmer than room temperature, but about room temperature. Okay. And we want to know what's the entropy produced. Well, to calculate the entropy produced, we need to figure out the heat transfer. And so we'll start with the first law to figure out the heat transfer. We know that dE dt is equal to Q minus W. This is steady state, so dE dt is equal to 0. These should be dotted. Those are rates. And so Q dot is equal to W dot. Okay, so that's just from steady state. And now we have to think about, so the way we're going to use this, we're trying to get to this rate of heat transfer. We're given powers, so those relate to the work. So we have work coming into our system of 60 kilowatts. So W dot is equal to, would that be a positive or a negative 60 kilowatts? I mean, at least that's an answer, okay, for all the rest of you deadbeats. Okay, so remember that for the first law, heat, energy, work being done by the system is positive, being done on the system is negative. So this is going to be negative 60 times 10 to the third. And then the 58 is going out. So we have plus 58.8 times 10 to the third. And so that's Q. And so Q is equal to negative 1.2 times 10 to the third watts. Okay. And so, I mean, that makes sense that heat is going to be coming out of this. We're not talking about heat being added to the system. So now we're going to go to the expression that says the change in entropy is equal to the integral from state 1 to state 2 of dq over temperature of the actual process all the way around the boundary plus sigma. And we'll think of this on like a per second basis because what we're really getting is rates. Okay, and now let's think about what this says. So if we're doing a cycle, like over 1 second, this is a cycle. All the properties stay the same. So what's delta S over that cycle?
That'd be negative 1.2.
Well, remember, that's what this integral is going to be. But remember that entropy is a property. Okay, so this goes to 0 because it's a property undergoing a cycle. That all just comes from the steady state, the fact that this is steady state. And now we can calculate this. Yeah, so we have 0 is equal to what's the heat transfer divided by the temperature. We know that the total heat transfer is negative 1.2 times 10 to the third. The temperature is 300 Kelvin. So each second we have a sigma equal to, what does that divide out to? 4 joules per Kelvin. And so sigma dot, that means, is 4 watts per Kelvin. This should have been Kelvin, not Coulomb.
Do you just ignore the integral because we weren't given state 1, state 2?
Well, this is like, so what I did was maybe state 1 and state 2, we can, in this case, think of it as like instant 1 and instant 2. We know how much heat was transferred between over that second. We know that it was negative 1.2 times 10 to the third joules. And so this integral just becomes the total amount of work. The reason we can do it as a total Q over T is because the boundary temperature is the same everywhere. If that boundary temperature was changing, it would be impossible with what we know. Yes,
So we just integrated for like 1 second, basically?
that's what we did. Yes. Just 1 unit of time, so that we can just go back and forth between a finite value or whatever and a rate. Any other questions about that? Okay, so that value, I mean, that's a really important thing for when you're designing a system. Say you're an industrial engineer and you're trying to figure out where your inefficiencies are coming out. You can do this calculation to all your processes, find out where entropy is being produced, and those are the places that are candidates for, the bigger that value is, the more of a candidate something is for reductions in inefficiencies. Okay. So this tells you the inefficiency in a real process. Okay, so far we've used entropy as a way to find inefficiencies. So far we've used entropy to measure inefficiency. There's one other thing that entropy can do that the first law of thermodynamics couldn't. So one other thing entropy can determine that the first law can't. and that is the directions of processes. So the second law of dynamics in its most basic form says that heat cannot spontaneously transfer from cold to hot. Okay. And so if everything was just spontaneous heat transfer, then we could already just use that idea of it to determine the direction of a process. You know, um, if there are two states, one is uh, 2 rooms at 60 degrees uh, Fahrenheit, and the other state is 1 room at 30 degrees Fahrenheit and the other room at 85 degrees Fahrenheit. Okay, you know that heat is not going to move in a way to make those temperatures more different. You know, it's only going to bring those two temperatures closer together, right? But let's see how this calculation shows us that. Okay. Um, so let's say I'm going to do this with an example. And let's say we have an isolated system. Which means there's no energy transfer across the boundary. Across the system boundary. Um, and let's say that we have 0.5 kilograms of steel initially at 400 Kelvin. And it's submerged in 10 kilograms of liquid water initially at 283 Kelvin. And we're going to do two things. We're going to first calculate the equilibrium temperature of the system. And then second, we're going to use entropy to show that equilibrium temperature has to be the later state, not the earlier state. So say this is going to come out to be, right around 300 Kelvin or whatever. What we're going to show mathematically is that it has to start with these two different temperatures and end up at that equal 300 Kelvin temperature. There's no way that you can put two 300 Kelvin things together and have those temperatures separate. Okay. It makes perfect intuitive sense, but now we're going to see for the first time how to calculate that. Um, so the first thing we're going to do for part A is we're going to use the first law. We're going to assume both of these are incompressible. And so the first law says the change in internal energy is equal to Q minus W. Since this is an isolated system, these are both 0. And so the total internal energy change has to be 0. Okay, so that's for an isolated system. So it's insulated, plus there's also no power coming in of any kind, no work coming in. And now for incompressible materials, how do we calculate the change in internal energy? So for incompressible, remember, the specific heat is equal to du dt. And so du is equal to c dt. And if you integrate those, you get that the change in internal energy is equal to C times the difference in temperatures. For steel, for solid steel, you can look up this specific heat and you get about 460 in SI units. This is joules per kilogram Kelvin. And for liquid water, this is about 4186 joules per kilogram Kelvin. So now we'll say half a kilogram times 460 times the quantity T2 minus 400 plus 10 kilograms times 4186 times the quantity T2 minus 283. That's the total change in internal energy is equal to 0. And if you go through that and calculate T2, you get the T2 is 283.6. So much closer to the water temperature than the steel temperature. There's a lot more mass of water and it has 10 times as much heat capacity. And so then for part B, what we're going to do is we're going to calculate the change in entropy for the steel and the change in entropy for the water. And since it's isolated, there's no entropy change due to this process outside of the boundary. So this has to be greater than or equal to 0. And we don't have time to do that right now, but we'll do that first thing next time. But what we're going to see is if you assume that the earlier case is the two objects being at different temperatures and assume that the later instant is them at the same temperature, you're going to satisfy this requirement. You're going to get a total entropy that's greater than 0. If you assume the opposite, that it starts out with them at the same temperature and the later instant is them at different temperatures, you're going to get a value that's less than 0, so you know it's not possible. Okay, that's all.
And the weekly one is due on Monday, right?
Yeah.
Okay.
Yeah, have you guys looked at that one yet? How did it did you have sort of a feel for how to go through it? This is the first time I've done those problems.
I'll just go get them